All right, let's jump right into it. Have you ever wondered how you take the chaotic physical world around us and translate it into lines of code? Well, in this explainer, we're demystifying Java's syntax by anchoring it to its real-world, object-oriented philosophy. We are going to look at how physical concepts literally become software.
We'll be moving pretty quickly today. We're going to map out the object-oriented philosophy, break down Java's basic building blocks, look at handling inputs and math, figure out how code makes decisions, and wrap up with the power of loops. So let's kick things off with that first piece, the object-oriented philosophy.
It's honestly a fascinating challenge, right? How exactly do we take physical stuff, like cars, plants, or even people, and turn them into digital data? I mean, older programming models were kind of obsessed with rigid procedures. But Java takes a completely different, way more intuitive route.
And here's the core of it. In object-oriented programming, data is king. Instead of letting all your information just float around chaotically, a program gets divided up into these neat, secure little building blocks called objects. These objects basically lock data together with the specific actions that use it, keeping the whole shebang incredibly safe and organized.
Just think about a real-world car for a second. Its manufacturer, its model, its color. In software, those directly map to the state or data fields. And its physical behaviors, starting the engine, stopping, changing gears, those become the methods in our code. It's literally a one-to-one translation of reality right into a software unit.
But here's the catch. You can't just build those digital cars out of thin air without a blueprint. And in Java, a class is exactly that. It's essentially an object factory. It defines the common properties and behaviors for a whole group. Once you've got that class written, you can use that single factory to stamp out thousands of unique individual objects right into your computer's memory.
And that brings us to a real game changer, inheritance. Think about the plant kingdom. Because herbs, shrubs, and trees all share basic plant traits, we only have to define those traits once in a base plant class. Then, if we create a derived class, say a tomato, it automatically inherits those features from herb, which got them from plant. This is absolutely crucial because it means you don't have to rewrite code. You just bolt on whatever's uniquely new to the tomato, and you're good to go.
Okay, moving on from the philosophy, let's look under the hood at Java's basic building blocks.
You see, every single variable in Java absolutely must have a designated data type. This dictates exactly how much memory it's going to use. We essentially have two paths here. First, independent primitive types. These are your lightweight, lightning-fast data pieces. And second, reference types. These act as memory addresses, pointing to much larger, complex collections made up of those primitives. Think arrays, or those classes we were just talking about.
Now, believe it or not, despite the totally endless complexity of the software you use every single day, there are exactly 8 primitive data types supported by Java. That's it. Just 8 basic building blocks to construct the entire digital universe. Crazy, right?
Depending on what you're building, you've got 4 distinct types just for whole integers, scaling all the way from a tiny byte up to a massive long. Then you have 2 floating point types for decimals, float and double. You've got char for single text characters stored using Unicode. And finally, Boolean, which just stores a simple true or false state. It's a small toolkit, but it covers everything.
So, we've got our data. Now let's talk about inputs and math functions. To actually get information from a user, like say asking for their age, you're essentially setting up a digital microphone. It's a simple flow. First, you import the java.util.scanner package. Next, you use the new keyword to create that scanner object in memory. And finally, you just tell it to read the input stream from the keyboard so it's listening carefully for those user keystrokes.
Once that data's in, there's zero need to reinvent the wheel for calculations. Java's standard library is packed with powerful math functions, so you aren't writing complex equations from scratch. Whether you need trig, like sine and cosine, quick max and min checks, exponential logic, or just simple rounding, you just call the math class, like math.square-root, and boom, you instantly have your square root. It is a massive time saver for sure.
All right, up next, making decisions in code.
Because, let's face it, a program isn't very smart if it can't make its own choices. The if-else statement is your fundamental fork in the road. It splits the execution path depending on whether a single condition evaluates to true or false. If it's true, the program takes one path, does its thing in block 1. If it's false, it totally bypasses that and executes block 2 instead.
But picking the right tool for the job really matters here. An if-else block is fantastic for broad, complex ranges, like checking if a test score is between 50 and 100. However, if you're checking specific, exact cases, a switch statement is your best friend. It only performs equality checks against a predefined list of integers or characters. Honestly, just think of a switch statement like an automated phone menu. Press 1 for accounts, press 2 for billing.
A quick warning though, watch out for a classic beginner trap. If you forget to include the break command at the end of a specific case in your switch statement, your code will literally just fall right through and execute every single case below it. It's a super frustrating logic bug that can take hours to track down if you don't know what you're looking for.
Now for the final piece of the puzzle, the power of loops.
A loop is basically an engine. It just keeps spinning through a block of code until a specific condition tells it to stop. To get it running, you need 4 main things: an initialization to set the starting line, a test condition so it knows when it's done, a body containing the actual work, and an update statement to push the loop forward, like adding 1 to a counter every time it spends.
In the timing of that stop condition, that is absolutely everything. We have entry-controlled loops, like your for and while loops, where the condition gets checked right at the beginning. If it's false on day 1, the loop body gets skipped entirely. But with an exit-controlled loop, like a do-while loop, that check happens at the very end.
So with a do-while loop, the loop body executes first, does its updates, and only then asks if it should keep going. Because that check happens at the exit doors, the code inside a do-while loop is mathematically guaranteed to run at least once, no matter what.
So, we've covered a lot of ground in this explainer. We've seen how OOP mimics reality, how primitive types hold those tiny bits of info, and how conditionals and loops drive the whole engine. Now that you've got this concrete understanding of how Java structures, stores, and executes data, the only question left is, if classes are your blueprints and loops are your engines, what incredible digital worlds are you going to build next?